So I wanted to start our discussion of parametric equations, just with a little bit of discussion about pictures, about graphing and stuff. First question is, though, what really are parametric equations? Well, we're used to thinking of functions, something like y is a function of x, right? But a lot of things that we're more interested in, and will be continued to be interested in, are not even really functions, right? If I draw a circle, a terrible circle, could be worse. Well, pretend it looks like a circle. Okay, we know what the equation of this is. It's going to be a unit circle, so it's going to be x squared plus y squared equals 1. But we also know it's not a function in the way it's written. It's not written as y is a function of x, right? I failed the vertical line test, for one thing. So if I want to use my calculator to graph the whole circle as y is a function of x, I have to solve for y. And I have two branches, right? I have the positive square root and I have the negative square root. Okay? Well, it turns out that this is something that happens a lot. And a lot of curves in space, in physics, all the time. If you're something moving with different forces in the x and y direction, you might have something which you want to do some calculus with, but instead of having a nice form like this, my graph looks, like some mess like that. And we don't know how to take the derivative if it's not a function. So what we're going to do is we're going to learn how to look at this, not as y is a function of x, here's x and here's y. But in fact, we can think of both x and y as functions of t. Show it, but this, how about that axis is y. Okay. And we can do that in various ways. But for example, for a circle, the easiest thing to do, in fact, we kind of already know it, right? We do definitely know it, right? If I think about this, and then I can call this theta, or I can call this t, I can think about going around the circle. And we know, well, the standard one is to let y be cosine of t and x be sine of t. And so, because then when t is 0, I'm starting at, no, the other way. Let's say it the other way. X equals cosine of t, y equals sine of t, right? Because then when I put in t equals 0, x equals 1, y equals 0, that starts us here. Now the other way also parametrizes the circle. You're just starting at a different point, going a different way. But this is the standard. And we know this is a circle because if I put these things in there, what do I get back? I get Pythagorean identity, right? X squared plus y squared equals 1, because cosine squared plus sine squared equals 1. Right. So there it is. That's the idea. To go all the way around the circle, I need to take my t from 0 to 2 pi. If I take my t from 0 to pi, I'll get the top half. If I only want one quadrant, I'll take that particular quadrant. But what we're doing here, most importantly, this is a parametric equation because both x and y are given as functions of the parameter t. Okay, so I've got x being x of t, y being y of t, and t has it going from someplace to someplace. Okay, so what I'm going to do now is just go on Desmos, and we're going to draw some other ones to give you kind of an idea of what's going on. Properly. Where is it? Oh, there we go. Here we go. Right. Okay, so for example, let me just tell you how you put it into Desmos. You have to think about these things as an ordered pair, x and y. So they want it like an ordered pair. So cosine of t, comma, sine of t, they want the x, y coordinates. And they will give you the t, their default is always t going from 0 to 1. But of course, we want t from 0 to 2 pi. And for some weird reason, I'm not sure why. Hold on, let me fix this. My little face is there. Okay, something a little bit easier to work with, right? Okay, I don't know why it was so small. Okay, but if you want to put in any parametric equation, you can go ahead and just put it in that form. Now let me do another one, just to do here. X equals 1 plus t, y equals 5 minus 2t, and I probably need to make that. Let's take t from minus 5 to 5, and I need to make my little self smaller there. There it is, right? So this is a line, and we'll show in a minute why that's a line, or how to get that it's a line and the regular XY coordinates of the line. But I do want to point out, so we can do stuff like that. Let me give you another one. One thing I want to point out about it is that though we are writing things in terms of t, you're actually drawing the I don't know what little line there. I'm trying to do two things at once, and I'm not good at doing two things at once. Let's see, 2 pi, and you know what? Maybe let's move that over. All right, well, fine. We'll just move the whole thing over. All right, there we go. So, we're drawing in the XY plane. The t is a parameter. It's not actually pictured. And that's one thing about Desmos. You might find if you use your calculator has a way of graphing parametric equations. And often with the TIs, they're kind of nice because they'll actually trace it out. For example, for this ellipse, similar to a circle, but C is slightly different. If I start from t equals 0, I'm here. And going all the way around, I go all the way around t equals 0, t equals 2 pi. Desmos just plops the whole thing there, so you can't really get that feeling for the fact that as you use time, t equals time, as time goes on, you're actually tracing out these different paths, okay? The ellipse is, of course, like a circle in a lot of ways. And one thing we can do is we can take different pieces of the ellipse depending on whatever time we want. For example, also for the t for the line, if I take less of it, whoops, equals, I don't know why it's minus there. Let's do 1 to 3. That gives us, say, that piece. Okay, it just happens to meet there. Okay, so you see, that is how that sort of thing works. Now, let me give you some other examples that are kind of interesting. I will say that the most important ones are the circle and sort of lines or a parabola. Once being able to draw something that you know as a function, being able to parameterize it. We'll talk about that. Oh, before I go on, I want to mention something else about the circle, actually. So I'm just going to do a different one, and I'm going to do a little bit bigger. But notice what happens if we do what I did by accident. And instead of going cosine t sine t, we do sine t cosine t. T equals 1, 2 pi. All right, it's still a circle. Okay, and if I change the 2 to 1, so that I had, so you see how that works, they're the same circle. So I parametrize the same curve 2 different ways. There's other ways I can do it. I can do sine 2t and cosine 2t, again, taking, I only have to go to pi. So all of these three are the same parametrization, are different parametrizations for the same curve. So unlike your usual y as a function of x, there are many different ways to parameterize the same curve. Usually, of course, we use the easiest one, or the one, like the reason we use this one is because it starts here and it goes around the unit circle, counterclockwise, the way we're used to doing our unit circle. But it doesn't mean that the other ones aren't good or whatever. It just happens to be that that's most useful. So I just want you to be aware of that. Parametrization of a curve is not unique. You can change the t, you can change the thing around a little bit. Depending on how it goes, they'll still give you a parametrization of the same curve. Another important curve, but probably not one that you'll see very much in Calc 3, but one that's sort of interesting from a historical point of view. Let me start from the beginning. Well, or I can just start from here. This is the cycloid. I was going backwards. But the cycloid is the curve that you get if you take a wheel and then you take a point on the end of that wheel and you let the wheel go on the straight line, and there you have the path there that is being drawn out by the point on the wheel. So this was like a big deal back a long time ago, right? Around the time Newton, Leibniz, and trying to figure out all these different things about math. They really liked this kind of problem. To figure out what the parametrization of this problem is, it's a little bit difficult. You can kind of see it over here. They've written it. I don't know if I can do it, but oh, no. They've written it here. Those are the equations. If you'd like to see how to find them, not only is it in your book, but I also have given you guys a video on it. It's kind of a neat geometric construction. I'm never going to ask you to do anything like that, so if you don't care, you don't have to worry about it. But it's sometimes neat to see these things. So I will also link this so that you can play with it. You can change the size of the circle and everything. It's 2 here. That's the radius of the circle. That's all. And you'll see the deal is, of course, as my circle goes all the way around, so the length here is the length of the circumference of the circle. Okay. So there's that. And then the next obvious question, if you're thinking about problems like this, all right, I have a circle that's going on a straight line. What happens if I have a circle that's rotating on other circles? So those are these rolling Hypo Cycloids. Let me, okay, I probably have to reload this. Well, hold on, there we go. Let's see, bump. Okay, it's working. All right, let's do one at a time. There's too many things here. So here you see 2 circles, one that's rotating on the inside of a circle and one that's rotating on the outside. So the outside curve is called an epicycloid and the inside curve is called a hypocycloid. You can play with this. You can, make the little circle smaller, right? And you'll see what happens, right? You'll have more little humps. So it's of course, very similar to the cycloid. You can make the bigger. Woo! This one's kind of interesting. Or even better, 1, n equals 1. This curve actually we'll learn about in polar coordinates as well. This is a cardioid. You see how it's a heart, right? So that's interesting. Well, it'll maybe not interesting. But then the other thing you can do, notice for both of these, I had my point on the end. Let me put 3 of them in here, 3 or 4, so we have something. My point on the end of the circle. Now, what happens if we look at a point in the middle of the circle? Okay, you're going to get something that looks like that. Okay, so these are all different curves that you can use parametric equations to describe. It's easier to describe them in terms of parametric equations than it is to describe them in terms of y and x or some other thing, theta, well, theta, So then that's just sort of to give you some idea of what you can do with these techniques.